In this video, I'm going to do an example of finding a standard deviation. The example says data on a sample of light bulbs reveals lifespans of each bulb as follows: in hours, 350, 425, 475, 480, 500, 520, 690, and 700. Those are the hours that a random sample of light bulbs last, the duration of their lifespan in hours, given by this data. The question is to calculate both the population and sample standard deviations. Now, our first step is to add up all the values and divide by the number of values, that is, to get the average. So the data was the 350, 425, 475, 480, 500, 520, 690, and 700, and this X bar represents the sample average. It's equal to, this is a sigma, represents the summation of all the data values. X sub I represents each data value. X sub I could represent x1, x2, x3, and so on for each of the data values, and I have n representing the total number of values. So this is the sum of the values on top, the number of values. If I add all these guys together, I'm going to get 4,140 divided by 8, and I get the average 517.5. That's the first step in finding the standard deviation. The next step is to create a table like this. What I've done in the first column is list each of the data values, and next to it I've listed the average of all those data values. And then in a column next to that, I'm going to take each data value minus the average. And so 350 minus 517.5, that gives me negative 167.5. Similarly, 425 minus 517.5, that's negative 92.5, and etc. on through the data. And what I'm doing here is calculating basically how far each data value is from the average, where negatives indicate a data value less than the average, and positives like these indicate data values above the average. What I want to do in the standard deviation is essentially calculate an average distance from the average of all the data. But if I added together positives and negatives, they could cancel each other out. And so the last column in my table here is to take each of these differences from the average and square them. That makes everything positive. So this is negative 167.5 squared, negative 92.5 squared. Each value in this column, all these differences are all squared and listed into this column here, the squared differences, you could call them. Now, depending on the question, whether they're asked for the sample or the population standard deviation, we'll either do one of these two formulas. So this question that I'm doing in the video, I'm asking for both, so I'm going to demonstrate both of them. So if we begin with the sample standard deviation, what I would do is, looking at this column of the squared differences, I'm going to add them all up and divide by one less than the number of values. That is, add every single one of these values, the sum. So the sum of the squared differences is the 28,056.25 plus 8,556.25 plus, and continue. All of this gives me 103,200. Now what I'm going to do is x minus x bar squared divided by n minus 1 for the sample standard deviation. That's 103,200 divided by, we've got 1, 2, 3, 4, 5, 6, 7, 8 values. So this will be 8 minus 1, 103,200. Divide that by 7, and you get 14,742. Now, this is the standard deviation squared. So the last step is to take a square root of that. To be a little more accurate, let's say 14,742.86. So the standard deviation is the square root 14742.86. It's about 121.42. That's my answer for the sample standard deviation. So perhaps I should have just written in my notes to begin with that it's actually the square root that's the standard deviation, and this is a square root. So I do these calculations in each of them and do a square root. So this is the answer for the sample standard deviation. Now let's go back and do the population standard deviation. Everything will be the same except I just divide by 8. That's the only difference. I'll divide by the total number of values instead of one less than the total number of values. I'll talk about why that is in a minute, but let's just work through that calculation. Okay, I'm going to talk through the steps of finding the population standard deviation. And just like for the sample standard deviation, I have a list of all the data. I have found the average of all that data using the total number of values. I do that for both sample and population. I use the total number of values to get the actual average. Then take each data value, subtract the average, find all these differences, and then take all these differences and square them. And here's where this formula comes into play now. It's the sum of all the squared differences. Now it's exactly the same thing that I just did in the sample standard deviation, adding up all these values. So I'm going to use the same symbol, sigma, for standard deviation for both sample and population. Here in my notes I'm not going to use different symbols, but now for the population standard deviation, take a square root of the sum of these squared differences and divide by the total number of values. So it's a square root, and if I add up all these values, just like we did in the sample standard deviation, adding up all these values, adding them together, and I get 103,200. And now I'm going to divide by the number of values 8. 1, 2, 3, 4, 5, 6, 7, 8. So now it's a square root of 103,200 divided by 8 is 12,900, and the square root of 12,900, about 113.6. So this is the answer for the population standard deviation. In each of these calculations for standard deviation, the units are going to be hours because the data represented hours. This was a lifespan of a light bulb, and so the units were hours. In the data, the units of standard deviation are hours. Okay, so I'll make a little summary here. I take all the data, which is in my left column, find the average, take differences from the average, and square all those differences. And then either I'm going to do a sample or population standard deviation. If it's the sample standard deviation, I follow this formula. Population standard deviation, I follow that formula. Now, on the top here, you see that I followed the formula for the sample standard deviation. I add up all of the squared differences and divide by one less than the number of values. In this case, there were 8 values, so I'm dividing by 7 and taking a square root of that result. For the population standard deviation, I'm adding up all the squared differences and dividing by the actual number of values, which was 8, taking a square root of that result. And this is my answer. Now what these really represent is the average distance of the data from the average. And the only difference in the calculations here is to account for the fact that if the data we have is a sample, it doesn't represent all the data, and there may be data values that are outliers, that are higher or smaller than the values that we actually got in the data, and therefore the actual data may be spread out more than what we see in the sample. And that's why we're dividing by one less here, is to make the result just a little bit bigger. So we're effectively calculating something that represents the average distance from the average, but we're pushing it up a little bit to account for the possibility that there are some outliers if we're only looking at a sample. If we're doing a population standard deviation, that would mean that we're actually looking at all the data as the entire population, and this formula is actually finding the average distance from the average of all the data values. Okay, that's the end of the example. I hope it was helpful.